These equations, along with the conversion of energy equation, form a set of coupled nonlinear partial differential equations. This is not possible to solve these equations analytically for most engineering problems. As you can see, the applications are just about endless with what you can do with CFD and the Fluent Programming. CFD is very attractive to the industry since it is more cost effective than physical testing.
So here in the design modeler, you can see a sketch of the airfoil. We designed this airfoil in ANSYS to resemble an airfoil used in a previous project. Its shape is unique, but that gives us unique results. The tail end of the airfoil had to be located at the origin of the grid, otherwise the method used for meshing would not have performed as well as it did. Here in the mesh geometry is our mesh structure of the airfoil. We started first by making a large area around the airfoil, which is the half circle and rectangle, and created a boolean to subtract the area of the airfoil away from the large area. We then divided this entire area into 4 parts, which gave us a hole where the airfoil is. This creates the rest of the space as a moving airflow. For setting up edge sizing, we used a common setting of 100 divisions per edge and biased the edge so that each bias was getting smaller closer to the airfoil. For the contour of static pressure, a design flaw is revealed. At the very front of the leading edge, we see a high pressure area. This indicates that the airfoil should be made thinner at the leading edge to allow for higher efficiency. We can see how the high pressure zone affects the rest of the wing by causing a low pressure zone immediately after on both the top and the bottom of the airfoil. A good design factor, however, is how thin and sharp the trailing edge of the airfoil was made. It can barely be seen that there is a little pressure increase where the 2 streams of air reunite. This airfoil could perhaps perform well in a dense fluid, such as water. In this velocity contour, the colors clearly show us what is happening. At the very tip of the leading edge, we can see a slow area where the incoming air is separating to be split above and below the wing. At the very top, we see a small yellow zone where the split air speeds up as it hits fresh incoming air. At the bottom of the leading edge, we see the same effect, only a bit more pronounced. Directly under the airfoil and directly after the bottom of the leading edge, we see a slow zone in that pocket, which lines up with what we see in the turbulent velocity flow. The results of this contour show us a turbulent kinetic energy. Since the speed of the airflow was roughly 20 miles per hour, there isn't a lot of turbulence. What little turbulence there is located right under the wing in a low pressure area. Here in the graph contour, we can see a large spike at the beginning and a bit of inconsistency in the start. As it progresses, however, it begins to smooth out and become a bit more uniform.